Welcome to Advanced Linear Algebra. Today, we are going to explore one of the most elegant and practical algorithms in mathematics, the Gram-Schmidt Orthogonalization process. If you have ever wondered how computers handle massive 3D environments or complex weather simulations without collapsing into rounding errors, the secret often lies right here. Let us dive in and see how it works. Before we look at any math, imagine you are building a large tent from scratch. If your wooden support poles are leaning in random directions, your structure will be weak and likely to collapse. You need a systematic way to plant the first pole firmly, then adjust the second pole so it is perfectly perpendicular to the first, and so on. In linear algebra, we often start with a standard basis of vectors that point at awkward angles. The Gram-Schmidt process is our mathematical straightening tool. It takes any ordinary skewed set of directions and forces them into a neat, perfectly squared off orthogonal basis, where every vector meets at exactly 90 degrees. Now that we understand what orthogonalization is, let us look at how it works mathematically. We start with a set of linearly independent vectors, v1, v2, and so on. Our goal is to build new orthogonal vectors, u1, u2, and so forth. We begin by simply locking the first vector in place. u1 equals v1. There is nothing to be perpendicular to yet. But for the second vector, v2, it is probably leaning toward u1. We must mathematically chop off that leaning portion. We do this using the projection formula. The fraction represents the inner product, which measures exactly how much v2 overlaps with u1. By subtracting this overlapping shadow, what remains is our new vector, u2, which is perfectly perpendicular to u1. This formula we just saw is much easier to understand visually. Look at the diagram on screen. The horizontal axis represents our first fixed vector, v1. The slanted arrow is our second original vector, v2. Notice how v2 casts a shadow down onto v1? That dashed line and the horizontal segment represent the projection, the exact amount that v2 is leaning in the wrong direction. The Gram-Schmidt formula calculates the length and direction of that shadow and subtracts it away. The result is the vertical arrow, u2. It is the pure, independent part of v2 that points straight up, forming a perfect 90-degree angle with our base. Let us see this process in action with a concrete example in two-dimensional space. We are given two vectors. v1 is 3, 1 and v2 is 2, 2. Our goal is to force these leaning vectors to sit at a perfect 90-degree angle. Following our algorithm, the very first step requires no calculation. We simply lock in our first vector. So u1 equals 3, 1. This is our foundation. Next, we need to find out how much our second vector, v2, overlaps with this foundation. We calculate the inner product by multiplying their matching coordinates and adding them together. 2 times 3 plus 2 times 1 gives us an overlap value of 8. Continuing with our calculation, we now need the squared length of our foundational vector, u1. We take the inner product of u1 with itself. 3 squared plus 1 squared gives us 10. Now we have all the pieces for our projection formula. We take our original v2, which is 2, 2, and subtract the fraction 8 over 10 multiplied by u1. 8 tenths simplifies to 4/5. Multiplying 4/5 into 3, 1 gives us the exact shadow vector, 12/5, 4/5. Finally, we subtract this shadow from 2, 2 coordinate by coordinate. This gives us our final orthogonal vector, u2, equal to -2/5, 6/5. These two vectors are now perfectly perpendicular. Now that we have successfully orthogonalized two vectors, let us extend this logic to the third vector, v3. The concept remains exactly the same, but now we have two established directions to worry about. To find our third perfectly straight vector u3, we start with the original v3 and subtract two separate pieces from it. The first fraction removes the shadow that v3 casts onto our first vector, u1. The second fraction removes the shadow it casts onto our second vector, u2. As we add more dimensions and more vectors to our space, we simply continue this pattern. We take the new vector and subtract its projections onto all the previously built orthogonal vectors, ensuring it stands perfectly perpendicular to everything that came before it. Now that we have our extended formula, let us take on a slightly harder problem with three vectors in a 3D space. Our starting vectors are v1, v2 and v3 as shown on screen. We need to find three completely orthogonal vectors, meaning they must all form 90-degree angles with each other, like the corner of a room. As always, we accept the first vector exactly as given. u1 equals 1, 1, 0. To find our second vector, we calculate the overlap between v2 and u1, which equals 1. Then we find the squared length of u1, which equals 2. We are now ready to chop off the first shadow. Continuing our 3D problem, we plug our overlap and length into the formula for u2. We subtract exactly 1/2 of u1 from the original v2. We distribute the 1/2 into the coordinates of u1, giving us the shadow vector 1/2, 1/2, 0. Now we subtract this shadow from v2 coordinate by coordinate. 1 minus 1/2 is 1/2. 0 minus 1/2 is negative 1/2. And 1 minus 0 is 1. This gives us our second perfectly orthogonal vector. We now have two vectors that form a perfect 90-degree angle, creating the base of our 3D corner. Next, we must fix the third vector. Moving forward to fix the third vector v3, we must find how much it overlaps with both of our fixed vectors. First, we calculate the inner product of v3 and u1. Multiplying the coordinates and adding them up gives us an overlap of exactly 1. Next, we find how much v3 overlaps with our newly minted u2. Carefully multiplying the fractions gives us an overlap of 1/2. Finally, we need the squared length of u2 for the denominator of our second fraction. Squaring each coordinate of u2 and adding them together gives 1/4 plus 1/4 plus 1, which totals 3/2. We now have all the pieces to assemble the massive formula for u3. With all our overlaps calculated, we are ready for the final calculation. We substitute all our pieces into the main equation for u3. The first fraction is simply 1/2. The second fraction is 1/2 divided by 3/2, which simplifies neatly to 1/3. We distribute these fractions into their respective vectors to find the two shadows that must be removed. After scaling, we subtract these shadow coordinates from the original v3 across all three dimensions. 0 minus 1/2 minus 1/6 gives negative 2/3. Doing the same for the other coordinates yields our final third orthogonal vector. Negative 2/3, 2/3, 2/3. We have successfully squared off the entire 3D space. Before we wrap up the math, there is one final step we often take. Making vectors perpendicular is great, but in mathematics, we usually want them to be orthonormal. This means they are not only at 90-degree angles, but they also have a length of exactly 1. We achieve this by dividing each orthogonal vector, uk, by its own length, which is called its norm, represented by the double vertical bars. Dividing a vector by its own length shrinks or stretches it, so its new length is exactly 1 unit. Think of it like taking a wooden stick of any random length and cutting it down so it is exactly 1 meter long. This gives us a perfect standardized grid. Now that we have learned how to build this perfect grid, you might wonder why we go through all this trouble just to make vectors perpendicular. In the real world, computers solve massive systems of equations for things like weather forecasting, artificial intelligence, and 3D graphics. When the vectors in these equations are leaning too close to each other, computers make rounding errors that completely destroy the final answer. By using the Gram-Schmidt process, we feed the computer perfectly perpendicular vectors, which makes the calculations incredibly stable and accurate. It is also the foundation of something called QR decomposition, which is a famous algorithm used by almost every software program to solve complex engineering problems. Let us review the key takeaways from this topic. The Gram-Schmidt process is a reliable mathematical recipe for turning any set of independent vectors into a set of perfectly perpendicular vectors. It works by taking one vector at a time and mathematically chopping off any part of it that leans on the vector we have already fixed, using projection subtraction. We can then orthonormalize them by dividing by their lengths. By building this clean, squared-off grid from scratch, we ensure that our mathematical models are stable, easy to work with, and ready for complex real-world computations. You now understand the complete Gram-Schmidt process.